At minus 45 degrees Celsius, a Mongolian pastoral family could not make winter disappear inside a G-air. The door still had to open. Smoke or combustion gases still needed a route out. The ground still drew heat from bedding and feet. The shelter's first defense was a circular wooden frame wrapped in felt and canvas, then tightened with ropes. The material you need to watch is the wool felt. Its fibers hold small pockets of air, slowing the passage of heat through the covering. You might answer by adding more felt. A thicker covering reduces heat flow through the walls and roof. But the G-air is not one continuous blanket. Warm air and combustion gases leave through the upper structure. Outside air enters around the door and through joints near the lower edge. Heat also moves into the ground beneath the family. Once those roots dominate, another wall layer gives less benefit than expected. Extra felt may improve one surface, while the heater must replace losses somewhere else. The covering, openings, floor, and heat source have to work as one system. If you follow the air, a central heat source starts the movement. The warmed air rises toward the crown, while cooler room air moves inward and downward to replace it. As that circulation reaches the felt, heat begins moving through the covering toward the colder exterior. This is where the wool performs its thermal work. Tangled fibers divide the air inside the felt into small spaces. Large air currents cannot move freely through them, so heat crosses the covering more slowly. Less energy reaches the outer surface each minute. The heat source can replace that loss more gradually, allowing the occupied space to remain warmer than the exterior. Ropes and fitted coverings work at the same time. They hold the felt against the frame while wind loads the outside. If the covering repeatedly lifts and settles, moving air can carry warmth out and pull colder air in. You limit that exchange by keeping the layers seated. Felt slows heat through the surface. Tension limits heat loss through temporary gaps. But the warmed air is rising toward the upper structure. One route has slowed, and the circulation has exposed the next. At the roof opening, heat control and air quality become the same problem. Heating arrangements changed across time and place. In stove-heated jurs, a flue carried combustion gases through the upper structure. The crown opening also served ventilation in documented jur forms. In either case, air leaving above had to be replaced. It entered lower down, around the door, the wall-to-ground seam, and smaller joints. Excessive leakage could pull a steady ribbon of cold air across the occupied level. The upper covering, therefore, did more than add insulation. Where the crown opening was used for ventilation, changing its exposure altered air exchange. In a stove-heated jur, the flue provided the main exhaust path, but leakage around the upper and lower joints still changed how much outside air entered. The physical connection remained. Greater outflow above required replacement below. That lower intake mattered because it entered where people sat and slept. Cold replacement air could reach bedding, hands, and feet before mixing with warmer room air. Closing the lower edge reduced the draft and reduced the amount of exterior air the heat source had to warm again. The doorway created the same problem in a place that had to open. A fitted door, and in some documented arrangements, a curtain, limited leakage while closed. When you entered, the opening connected indoor and outdoor air. Once closed, the barrier had to seat against its frame. The upper exit and lower door remained parts of one moving column. Each opening created a short thermal event. Outdoor air entered, indoor air was displaced, and the source had to restore the difference. A barrier that closed tightly shortened that recovery and prevented the wall's insulation from being bypassed. Even after infiltration was reduced, the ground continued taking heat from everything touching it. Felt flooring, carpets, and bedding placed fibrous layers between people and the colder surface below. Those layers trapped small pockets of air, as the wall covering did. If you trace the energy, it moved downward from warmer bodies and objects into the ground. Interrupting that contact slowed conduction. The soil did not become warm, and the entire floor did not reach one temperature. Instead, the household protected the places where people sat, slept, worked, and placed their feet. Another roof layer could not protect a body touching a colder surface below. Insulation had to interrupt the root at the point of contact. That local protection shaped how the room was used. Air temperature alone did not define comfort. Distance from the source, exposure to a draft, and contact with the floor all mattered when people placed work, rest, and bedding. This also explains why one thermometer cannot describe the whole gur. Field measurements show that indoor temperature varies by position. Felt seams, gaps near the door and wall, ground conditions, and solar exposure all changed the local result. You could feel a different thermal environment after moving only a few steps. Wind then tested every joint at once. The circular lattice wall and sloping roof divided the structure into many short supported sections. Roof poles carried loads between the crown and wall. Tension bands and exterior ropes held the covering against the frame. As you follow a gust, the round wall offers no single broad face, while connected pieces share the pressure. That geometry helped the lightweight frame resist wind loads. For heat control, a covering that stayed seated opened fewer temporary channels through the envelope. Each rope, therefore, had a thermal consequence. It restricted movement. Restricted movement limited infiltration. Lower infiltration reduced the energy needed to restore indoor air. Wind pressure changed from moment to moment around the structure. A covering that remained tight kept brief leaks from becoming continuous exchange. Structural and thermal stability were linked by movement of the envelope. That relationship was essential because a GER could not depend on the mass of a permanent building. Its lattice, poles, felt, coverings, and bindings had to be dismantled and transported. For Mongolian pastoral households, portability was practical. You could pack, move, repair, and assemble the parts again. The same lightness that enabled movement limited heat storage. The central heat source answered that limit by placing new heat close to the occupied space. In one circular room, people were not separated from it by corridors or thick interior walls. They received radiant heat from the source and convective heat from moving air. Cooking, warming water, work, and rest could remain near the same thermal core. Although equipment and fuel varied across periods and households, the interior was never a uniformly heated box. Radiation could warm a person near the source before the air and surfaces elsewhere responded. Floor coverings reduced contact loss where people sat or slept. Above, warmed air moved toward the crown. Around the perimeter, fitted layers and lower seals resisted replacement air. The family occupied the middle of several linked controls. A weakening fire or cooling stove reduced new heat entering the room. Heat already stored in the air, furnishings, and wooden frame continued leaving through the felt, joints, floor, door, and necessary air exchange. The felt slowed that flow, but the lightweight envelope held less energy than thick earth or masonry. When the source was restored, the small interior could respond quickly because little structural mass had to be reheated first. The same sequence shows you that rapid cooling and rapid reheating came from the lightweight construction. The felt was a brake on heat loss, not a battery that stored the night. If careful history matters to you, like the video and subscribe to Birch. A fixed adobe or masonry dwelling made a different thermal trade. Its walls absorbed more energy while the interior was heated. You would wait longer for the room to warm because the source was also heating the structure. Once warm, that mass could continue returning stored energy after the fire weakened. That stability required weight and permanence. Thick earthen walls could not be folded, loaded, and moved with a pastoral household. A GER used less thermal mass so its frame and covering could travel. It relied more heavily on slowing losses, concentrating activity, and restoring heat as the source declined. If you compare the constraints, neither design solved the same problem in the same way. A fixed structure could smooth temperature changes through mass. The GER could be dismantled, transported, reassembled, and reheated without first warming heavy walls. You can track that trade in the household's relationship with time. A massive wall rewarded long, continuous heating because the structure itself became part of the thermal reserve. A lightweight GER rewarded quicker correction. When the source weakened, the room responded sooner. When heat returned, the occupied space responded sooner as well. Portability and thermal inertia were not separate features. They were consequences of the same material decision. You can reconstruct the full circuit in one view. Wind reaches the curved, tensioned covering, which stays close to the frame and limits pumping through gaps. Heat crossing the felt is slowed by trapped air. At the lower edge and door, fitted barriers restrict cold replacement air drawn by outflow above. Floor layers reduce conduction where bodies meet the ground. The central source restores energy still being lost, while the upper opening or flue provides the exhaust path required by the heating arrangement. When one control weakens, another part works harder. A loosened covering allows more infiltration. A larger, uncontrolled opening draws more replacement air. An exposed floor keeps taking heat through contact. A fading source leaves the lightweight envelope with little stored energy to return. Extra felt on the wall cannot stop losses through openings and ground. You now know why no single layer explains the shelter. At -45 degrees Celsius, The GER did not stop heat loss. It reduced several routes until the household could keep pace with them. The structure supplied the frame, felt, tension, and controlled boundaries. The family supplied fuel, timing, placement, and attention. Together, those parts maintained an occupied interior without turning a portable dwelling into a permanent building. Outside, the wind continues pressing against the felt, and the temperature remains far below zero. Inside, you would not find a uniform bubble of comfort. The floor near a seam, the area beside the door, and the air near the crown can behave differently. What matters is that the household can recognize those differences and respond before the entire room follows the exterior. Before dawn, the heat source is fed again. Warmth returns first to the people and surfaces closest to it, then spreads through the occupied space. Bedding remains separated from the ground by felt and carpets. The door stays closed against unwanted air exchange, while the upper exhaust path continues serving the heating arrangement in use. The GER's construction belongs to Mongolian pastoral traditions that remain living practices. Its performance did not come from one miraculous material. It came from accumulated knowledge about felt making, wooden framing, tension, openings, flooring, placement, and daily use, taught and rebuilt across generations. Birch lays the felt sample across his open notebook, closes the cover over it, and leaves one hand resting there. The cold remains, but the family reaches morning together.